So, good day. We will begin our lesson in I3341 Advanced Algorithms. This course is given by me, Dr. Sabah Haidar, and by Dr. Antonia Yaoub. The textbook for this course is Competitive Programming 3 for Drs. Halim, and this is the outline of the course chapters as per the textbook. 1. Introduction. 2. Data structures and libraries. 3. Problem-solving paradigms. 4. Graph. 5. Mathematics. 6. String processing. And 7. Computational geometry. It continues for advanced topic as 8 and 9. Now we will see Chapter 7, Computational Geometry. Typical issues with geometry problems. You have to do a lot of tricky corner test cases. You have to check for example, a vertical line because it has an infinite gradient. You have, before calculating anything over polygons, you have to check whether the points are collinear. Where you have to check if a polygon is a concave polygon because maybe some procedures won't work. So you have a case where the convex hull, it's the last point we see it and discuss today in this chapter, of a set of points is the set of points itself, a geometrical problem, and that's why programmers think that geometry problems are the most complex problems we can encounter because of those tricky test cases. And add to this, you have the issue of the floating point precision error. We mentioned this in many courses. The floating point is not very precise in its digital representation, and the coding is tedious. So most of the papers you see in competitive programming, the paper material programmers bring with them are paper materials concerning this chapter we are studying together, concerning the formulas in geometry and the special functions. Chapter outline. So this chapter is mainly divided in two parts. First, we will discuss geometry basics. We will introduce a point, how do we represent it, a line, a circle, a triangle, and finally a polygon. And along with their functions, with the main functions that deal with these types. For example, how having 2 points, how I can get a line, how can I define a line, how can I define a circle, how can I know if a point is inside a circle, what is the perimeter of a triangle, etc. So all the elementary functions that deal with these types. The second part of this chapter will be essentially about 2D polygons, and we will cover convex and concave polygons, the case where we can check a point if it's inside or outside a polygon, the cut of the polygon with a straight line, and finally the convex hull. Not discussed in this chapter, the quadrilaterals in detail. We don't discuss 3D objects like spheres and so on, or others like cones, cylinders. We don't discuss plane sweep techniques, neither intersection problems or divide and conquer in geometry problems. Divide and conquer will be a chapter apart, and maybe we discuss geometry problems that require divide and conquer inside this chapter. The principles. Whenever possible, you must first highlight special cases before you proceed to implement any function. You have to always prefer test predicates. You have to prefer functions that returns yes or no over computing the exact numerical answer. Okay? If you don't need the exact numerical answer, don't compute it. As for the floating point operations, avoid as possible divisions, square roots, because they are heavy. So operate over integers. And whenever you want to test for floating point equality, the key issue here is to test whether their difference is less than a certain small epsilon. Do this test if fabs of a minus b is less than epsilon instead of if a equal b. Geometry basics. So we begin our first part of this chapter. As we said, the first part is about geometric basis and basics, and second part about polygons. So first we have to represent a point, because every geometric shape is defined by the points the points it contains. So how do we represent a point? We use, whenever possible, the two-dimensional point type, which is point underscore I. Why we say point underscore I? Because the coordinates of this type are represented in integer. So the advice here is to represent point underscore I instead of point which coordinates is double. So we have two classes or two structures, whether you are working in C or in C++ or in Java. So you have two types, point underscore I and point. So point underscore I will work with integer, and this is a very basic raw form. It is minimalist mode. If the problem does not require the other type, just stick with this type. It will work for you. The other type that we will continue with during this lesson is the general point type, which in fact is composed of two coordinates, the x and y of type double. So for this type we have a constructor, a default constructor that sets these coordinates into the null value, and the user-defined constructor. We have to mention here, because this is the first chapter that is going to be registered, that the coding, whether it is in Java or in C++, it is not really an object-oriented coding. This is a coding that is used for fast computing. So we don't really care about encapsulation, about inheritance. We don't care about the best techniques. We only care about implementing a function that gives us a quick result. I will show you here, for example, the book codes. So for example, our textbook is here. You have the codes used in the chapters, and here I am in chapter 7, geometry, and you have provided with the book the codes, the library used in chapter 7, and as you can see, for each file you have three languages: CPP, Java, and ML. Okay, so we have circles, points, lines, polygon, and triangles. You, with your workplace, you take the corresponding files. I took the Java files, I put them inside a Java project so that I can see them. You see? And today we will study each, and we will visit each of the functions here. The same thing with C++ developers, so the students who would like um, to work with CPP, so they can create their project and bring the CPP files in their space. On my Mac, I had a trouble including std C++.h, so I had to download it and then include it. But I think since it's mentioned in the book that this include is accepted by the competitive programming competitions. Back to our lecture, and here is our point, and from this example I will go back to Java code, which I will continue with during my lecture. So every time I have to refer to the code, I can refer to Java code. To mention that in the slides provided by the textbook, the reference is for CPP. So now you have two different languages explained. In my slides, we have the Java code, and in the textbook slides, we have the CPP code. And I can assure you it's exactly the same code, almost exactly the same code. So let's go to check our point type. It is in here. So our point underscore I, which is a very minimalist class. It contains only two fields and two constructors. And the other also small class, which is a point class. It contains also two fields, two constructors, and one overriding compared to method. Okay, so here the book has defined the class point as an inner class for the bigger class, which is points and lines. This is not an issue. That the programming details here are not the very optimal, but we already, and I repeat now, what we want is the efficiency of the code and not the design and not the conception. Okay, so we want a code that runs and gives us quick answer. That's why I will stick with the author's library, and we will not apply big changes. So this is our class point, and here we override the method compare to, because class point, as you can see, implements comparable point, and for the one who knows Java, this is the interface that is used for sorting among other utilities, and this is a very important method that is implemented here, overridden here, and it says whenever you are going to compare this point with another point, you compare first, as you can see, the axis, the x value, the x fields. And as you know, we already mentioned that we don't use equal operator or different operator with floating point. This is because we know already we will have precision errors, so we will compare whether the difference is greater than epsilon. So this is an alternative of saying if this dot x is different than other dot x. So if they are different, you return the ceiling of their difference. If they are equal, you then compare the y's. If the x's and y's are equal, you return 0. Otherwise, you return also the ceiling of their difference. So this compare to will be used whenever we want to sort a set of points. We simply call collections.sort, and because we have overridden this compare to method, the sort is given to you for free. Isn't this nice? You don't have to memorize any sorting algorithm. We continue with our library. Here is our Occlusion distance. It is the square root of the x2 plus y2. of delta x to the power 2 plus delta y to the power 2, and here is your beautiful code written, and math hypo returns the square root of its parameters addition but power to 2. So just exactly what we want. Hypot. Another topic we can do with only a point is when we have a point and we want to rotate it. If we want to rotate a point by an angle theta, counterclockwise, if we don't mention in which direction we want to rotate, it is by default counterclockwise, in the opposite direction of the clock. So around the origin O, you give a theta angle and you say, I want to rotate this point by a theta angle. How do you obtain the new abscisses of the new coordinates of the rotated point? You use cosine minus sine cosine matrix, and you multiply it with the vector of the original point coordinates. And here is our function rotate. It takes a point, it takes a theta, and this theta angle you are giving it in degree. Before we do the rotation and we apply this mathematical formula, we have to transform the degree value of theta into radian. So we are going to simply multiply by pi and divide by 180, and in order to do the opposite operation, so to from radian to degree, we multiply by 180 and divide by math.pi. And here we go. So we have here return new point, and to this user-defined constructor I am giving two parameters. The first is x prime and the second is y prime. For x prime I have the value cosine theta times x minus sine theta times y. This is x times cosine radiant and minus y times sine radiant. And for y I have x times sine radiant plus y times cosine radiant. And here I have my new point that I will return. Lines. So once we represented a point with its two coordinates, whether integer or double, we move to represent. How do we represent a straight line? A straight line, you are used to the equation of the form y equal mx plus c, which is not very good because it does not take into account the special case where the line is vertical. So in this case, the slope will be infinite. And instead of using this representation for a line, the better representation is to use a times x plus t, b times y plus c equals 0. So all the parameters a, b, and c from one side. And this is the beautiful representation. And every line equation can be written under this form, and this is an example. If you have y equal 3/4 x minus 1/2, it can be written when you multiply everything by 4 and you move before the equal sign, you will obtain 4y minus 3x plus 2 equals 0. So in this case, our line is represented by the following triplet: a equal 4, b equal minus 3, and c equal to 2. So the poor line equation is this form, and we have the representation in the class line 2, but is in fact never used. Instead, we are using this representation, and it is called the type line, and it is a very small type containing three double values. Points to line. Now we will see the function points to line, which takes 2 points and fills the fields in the third parameter, the fields A, B, C of the object L of type line. So, having 2 points P1 and P2 of respective coordinates x1, y1, x2, y2, we have to deduce the formula ax plus by plus c equals 0. So we do a simple mathematical operation, equation 1 minus equation 2. We eliminate the parameter c, and we obtain a delta x plus b delta y equals 0. We have two cases here we have to distinguish. In case of a vertical line, we will notice that the delta x is equal to 0. Here in floating point operation, it will be less than an epsilon value. In this case, we set a to 1, sorry, not a to 0, we set a to 1 and b to 0, and c, we replace the values, we will get c equal minus x1 or minus x2, which are the same thing. Else, in this case, we will be fixing b to 1. We will always have in the line equation the parameters a, b, and c. The b field is always fixed either to 0, either to 1. It is 0 in case of a vertical line, otherwise it is 1. And then we calculate the value of a, which is negative delta y over delta x, and consequently the value of c, which is minus a times x1 minus y1. Attention here, why do we have an if else? Because in the else we are going to divide by delta x, and if delta x is 0, or we will get an infinite number. So this is one of the places where we have to make sure we tested the corner cases. Another function or another two functions are the interaction between two lines. We can check whether two lines are parallel if we are given two lines L1 and L2 of type line. It means they are objects that have the fields A, B, and C, and we want to know if they are parallel. We just check if they have the same A and the same B. Whether it is the same line, we have to check the parameter C also. Function R intersect returns true in case line 1 and line 2 do intersect, and in this case it fills the field of the third parameter P, the x and y fields, and it returns false in otherwise. If the lines are parallel, so this function returns false. Otherwise, we have two equations in which we know the ABC parameters, but we don't know the x and y value, which is the same point, the intersection point. So what we do is 1 and equation 2 times b1 minus the reverse, equation 1 times b2, and this is how we eliminate the b values, and this is how we get x equals to b2c1 minus b1c2 and over a2b1 minus a1b2. As for y, we have to distinguish two cases. In the case one of the line was vertical, it will have a b that is equal to 0. In this case, it is better for us not to use this equation to obtain y, because we will have a division by 0. In the other case where b is not 0, it will be necessarily 1. So we will obtain y by replacing the value of x in one of the two formula according to which one is not a vertical line. We may have two non-vertical lines, so in case b1 is not null, use the equation of 1 to obtain the value of y, which in this case will be minus ax plus c, and we know x now. Otherwise, use the equation 2. We move to segment and vector, and we define a segment as a line with two endpoints. So a segment is not a continuous line until infinite. It has two endpoints, and this is called a finite line, and it has a finite length. A vector is the same thing as a segment, but it has a direction. So here is an example of a vector AB, where A is the tail and B is the head. And this is a class vec defined by the length over the x-axis of this vector and its length over the y-axis. So in fact, a vector, it does not matter which 2 points define it, as long as we have its length axis, its x length and y length. So this is a direction. This is the important thing. How to obtain a vector? Once given 2 points A and B, I can return the new vector, which is the difference of the abscissa and the difference of the ordinate. Two other functions, scale and translate. You can scale a vector into to be shorter or longer, or to remain the same. So you give the double scale ratio and the vector you would like to scale, and this function returns the resulting vector, and it simply multiplies the x length by this scale as well as the y length. The translate, you translate a point through a direction of a vector, and it returns the resulting point. And how do you do it? You add the abscess of the point to the x length of the vector, and the ordinate of the point, you add to it the y length of the vector, and those two new coordinates will form the new point you are going to return. Topic between the vectors is the operation of the dot product, which is a very simple and very important operation. Given two vectors u and v, the dot product is a very simple operation. It is noted u dot v, and if you have the fields a, b, and v, c, d, so u dot v will be a times c plus b times d. What does this operation means? This is a scalar value that is obtained, so the dot function takes two vectors and returns a double. This value, it indicates the following. If this returned value, the dot product, is positive, then we can conclude that these two vectors form an angle that is acute, and if this scalar value is null, it means that those two vectors u and v, or here in the schema you can see them represented as vectors capital A and capital B. If the dot product is null, it means they are perpendicular, they form a right angle, and if it is negative, it means, like here on the right of the slide, it means that the angle is obtuse. Distance to a line. So we will use somehow the dot product in the mathematical demonstration. It will be used to calculate the distance from a given point P to a given line defined by 2 points inside this line A and B. So distance to a line will take parameter B, parameter, sorry, P, A, and B, and it will returns the distance from P to the line AB, and it will return also the intersection point, so the point where this distance were calculated, the intersection point between the projection, the orthogonal projection of P onto the line AB. And the formula, the mathematical formula says that you have to calculate the double value U, which is the dot product between AP and AB divided by the normal square, which is the to the power 2, the add to the power 2, which is given a value V. It is V time V dot X to the power 2 plus V dot Y. Okay, so this value U, which is the dot product divided by the normal square, if you use it, okay, if you use it, how do you obtain the point C? You obtain the point C, it is nothing else but the translation of the point A. Okay, you translate it. How many unit? You translate it according to a vector. How do you get this vector? It is the scaling of the vector AB, but with the scale ratio you just calculated. So this is an easy math formula, but we are not going to demonstrate every math formula we will encounter. This way we will not finish the lesson, but I'm explaining it rapidly. So you obtain the value, the point C here, and what is the distance from P to line AB? It is the distance from P to C. So we will return the distance from P to C, and this is a function that we already have already written, and that also, and now normal square also, translate and square, all are already written. Distance to a line segment, this time we have also the points input point P, input point A, and input point B, and we want to calculate the distance from the point P to the line segment this time, and not the line AB. So we have also to create the vectors AP and AB, and we calculate the scalar value U, which is, like before, the dot product of AP, AB over the normalized square of AB, and we will get the value of U. We will examine the value of U. If it is less than 0, so it means that P is the closest to A, so the C value, the C point will be nothing but A. I will create a new point with the A value, and I will return the distance from P to A. Otherwise, we have two possibilities. U is greater than 1. So in this case, it is the opposite. The closest point to P is B, and we will return the distance between P and B, and C will be a clone of the point B. And if the value of U is between 0 and 1, so we will trace the orthogonal and we will find the distance just like we did before. We will find the point C. We will simply call distance to line, and it will return us the point C and the distance. Calculate an angle given 3 points A, O, and B. We have to calculate. We know that the dot product of the vectors OA and OB are given also by another method. It is at the same time just like defined before, but also it is the scalar length of OA times OB, scalar length of OB times cosine theta. So to obtain theta, the angle formed by these 3 points, we can calculate the arc cosine of the dot product of OA and OB divided by the length of each of the vectors. And here is the mathematical formula. Return arc cosine of the dot product of OA OB, given that OA is 2 vector OA and OB is 2 vector point O, point B, and divided by the root square of the normal square of OA times the normal square of OB. Interesting title before we finish this section and move to circles. The cross product. We saw the dot product. Now we will see the cross product, the counterclockwise and collinear points. So if we have a line PQ and a point R, if you want to know if whether R is on the left or the right side of the line, or perhaps maybe R will be collinear with P and Q. So this is a question in this slide. So we will form the vectors PQ and PR, and we will calculate the cross product. The cross product PQ cross PR is a vector. This is not a scalar value like the dot product, and which magnitude is equal. This vector is orthogonal to the plane formed by PQ and PR, and its magnitude is equal to the area of the parallelogram span. If the magnitude of this vector is positive, then we can say that P, Q, and R is a left turn. It means that R is on if we go from PQ to R, it is counterclockwise. If this magnitude is 0, this means the 3 points are collinear, and if this magnitude is negative, less than 0, that means that P, Q, and R form a right turn and they are in a clockwise position. And these 3 functions we will use later in more than one operation. Cross product, given 2 vectors A and B, the cross product is to return the magnitude of the cross product is A dot x times B dot y minus A dot y times B dot x. And to see if 3 points are counterclockwise, we check whether the cross product of those 2 vectors is positive, simply. So return cross is positive of 2 vector PQ and PR. And to see if the 3 points are collinear, we return whether the difference between the cross product and we return whether the cross product is less than epsilon. So this means the cross product value is almost 0, so this means they are collinear. Circles. Another section, circles. So a circle has a center and a radius. The center is a point. It has coordinates A and B, and it is usually defined by being the set of points x and having coordinates x and y that satisfy the following formula: x minus a to the power 2 plus y minus b to the power 2 equals radius to the power 2. We define now the function inside circle, which given a point P and a circle defined by its center and its radius. Notice that we are using here the integer representation of point. This function must return 0 if the point is inside the circle, 1 if P is at the border of the circle, and 2 if the point P is outside the circle. What are we doing? We calculate gx, which is the difference between the axis, dy is the difference between the ordinate of the point P and the center C, and the Occlusion distance is, we calculate the distance, which is dx times dx plus dy times dy. This is um, the Euclidean distance to the power 2, because the Euclidean distance is a root square of this value. And then we calculate r to the power 2, and we compare these two values, and we check if Ec is less than r square, then we return 0. Otherwise, we see if it is equal, we return 1, and otherwise it is outside the square, so we return 2. Other useful formulas and definitions. If you want to do precision calculation, don't use the pi of mass, but replace the value of pi with the expression 2 times r cosinus of 0.0. We know that the diameter is twice the radius. We know that for a circle the circumference is pi dot times the diameter, and the area is pi r to the power 2. Other values are arc, an arc given an angle um, alpha. So what is the length of the arc? It is alpha over 360 times c. What is c? C is the circumference of the circle. The chord is given also. This is the chord. What is a chord? If you cut the circle in two places, the segment that relies those two points is called a chord. And if you want to calculate, if you have a problem and you want to calculate the length of this chord, it is the square root 2 times r to the power 2 times 1 minus cosine alpha, alpha being the angle that is formed by this by these 2 points on the circle. If you have a sector, what is a sector? You can see a sector here. This is the part of the circle that you cut, forming an angle alpha, and it is easily calculated. It is a portion of the area, of the complete area, according to the angle alpha. The segment area, having an angle alpha and a chord, what will remain from the triangle? The part, it means the sector minus the triangle, will form what something we called segment. If you want to calculate the segment area, it is given by the sector minus, of course, the area of the isosceles triangle with sides r, r, and the third side length is chord. You can find other useful formulas for those values in degrees and radians on the different websites. I gave you a specific link here. Another kind of problem with circles is when you are given 2 points, P1 and P2, and a radius, and you want to calculate the centers C1 and C2 of the circles of radius r that can pass by these 2 points. This is a mathematical formula that you obtain by which you obtain the first center, and if you want the second center, because as the schema shows, you can have two circles passing by points P1 and P2 with the radius r. You just revert the order of P1 and P2 in the call. Triangles. In the basics, we continue under the title triangle. A triangle is a polygon with 3 vertices, 3 edges, and whose area is equal to the base times the height and multiplied by 0.5, it is the half of the area of the rectangle or of the parallelogram formed by those 3 points. The perimeter is the sum of the 3 edges lengths. By Heron's formula, we can obtain that we can deduce that the area of a triangle is a square root of s times s minus a times s minus b times multiplied by s minus c, where s here is half the perimeter. Okay, so this is safer for overflow formula, the same formula, but we distribute the square root over the different multiplications. But of course, this version is slightly more imprecise. You can calculate the perimeter of a triangle by returning the sum of the 3 sides. We can calculate the perimeter given 3 points. So you calculate the distance between these respective 3 points, and then you add them. If you have the 3 sides and you want to calculate the area of the triangle, you just apply Heron's formula. And if you have the area you want to calculate it given the 3 points, you just calculate the respective distances between the 3 points and you call the previous area function. Types of triangles: we distinguish equilateral, 3 equal sides, 3 equal angles; isosceles with 2 equal angles and 2 equal sides, of course; and scalene, different side lengths and of course different angles; and the right triangle. In circle function, given a triangle, sometimes you are asked to return the center and the radius of the end circle that is inside this triangle, and you have the formula and you can apply it to get the end circle, which is the inscribed circle function. Its radius is equal to the area of the triangle divided by the semi-perimeter, and that's how we calculate the R in circle given the length of the 3 sides, or given the 3 points. In this case we call the previous function. And we are also given that the location, the center of this in circle is the meeting point between the triangle's angle bisectors. So the bisectors of each angle, they have a meeting point. So this meeting point is the center of the encircle. We can calculate the meeting point of 2 of them. It is sufficient. And the meeting point, we already know that we calculate it using our intersect function. Similar problem. The circumcircle is the circle that passes in which the triangle is included. So the incircle is the circle included inside the triangle. Another kind of problem, we may want to calculate the circumcircle. The radius is equal to A times B times C over 4 times the area, and the center is the meeting point between the triangle's perpendicular bisector. So first you trace 2 perpendicular bisectors and you calculate their meeting point. So this is the code for the circumcircle, and that's it. Another thing is triangle inequalities. If you have three, let's say three values and you want to check if those three values are correspond to triangle sides, you just have to check the triangle inequality. Each summation of two sides must be greater to the third, or if you have them ordered from A to C, you would have just to check if A plus B is greater than C, and the three values can be the length of the triangle. Also, trigonometry recall, the law of cosine is equal if you have a triangle ABC, the scale and triangle like here, you know that C2 is equal to A2 plus B2 minus 2AB cosine gamma. And the law of sines, what does it say? It says that A over sine of alpha is equal to B divided by sine of beta is equal to C divided by sine of gamma, and is equal to 2r. R is being the radius of the circumcircle we just saw. Pythagorean theorem applies to the right triangle and is a derivation of law of cosine, where cosine of 90 degree is 0, so we will have C2 is equal, for this angle, the opposite side square is equal to the summation of the square of the two other sides. And we call a Pythagorean triple. ABC is the 3 points ABC where such formula applies, where C to the power 2 is equal to A to the power 2 plus B to the power 2. So if we know that also, if A, B, and C are a Pythagorean triple, then so is K times A, K times B, K times C for any positive integer K. A small recall about quadrilaterals. Nothing differs in the library. There is no special things for the library, but in a rectangle you have 4 right angles. In a square you have 4 right angles plus equal sides. In a trapezium you have 2 parallel sides, opposite parallel sides. In a parallelogram, each 2 opposite sides are parallel, and it applies each 2 opposite sides are also equal. In a kite, each two consecutive sides are equal. Every 2 consecutive sides are equal. We have equal, equal, and then equal, equal. And a rhombus, we have 4 equal sides, but not necessarily right angles like a square. And we finished the part 1 of the lesson. Part 2 is a more interesting one, but it was not possible to explain it without passing through part 1.